So, today we're going to be discussing one of the most important principles in quantum mechanics, the Heisenberg's uncertainty principle. So, let's give it up for the star of this episode, Werner Heisenberg. What has he done to deserve this honor? Well, he showed us that there are qualities of this world that we thought were real, qualities of this world that we thought we could gain access to, qualities of this world that we thought we could measure that we really can't. That measuring those qualities is a remnant of an old classical concept that he came and completely threw out the window with this principle. Now, what does this principle say? It says that there are a variety of mathematical inequalities which show us that there is a fundamental limit to the degree of accuracy with which we can measure these physical quantities. What does this mean? Well, he took a certain set of physical qualities and he divided them into two lists. Each quality in list 1 has a corresponding quality in list 2. He said that at any given point in time, we can only know half those qualities accurately. If we know half those qualities, i.e., the qualities in list 1 with a high degree of accuracy, we don't know the qualities of in the corresponding qualities in the list 2 with just as much with just as less a degree of accuracy. The more accurately we know the qualities in list 1, the less accurately we know the qualities in list 2. And the more accurately we know the qualities in list 2, the less accurately we know the qualities in list 1. So let's focus on the example that everybody focuses on, which is the relationship between the position of a particle and its momentum. Now, according to what we've discussed so far, the uncertainty principle says that the more accurately I know the position of a particle, the less accurately I know its momentum. And the more accurately I know its momentum, the less accurately I know the position of the particle. In another way to put it, and that is the way that most people put it, is that the more uncertainty there is in the position of particle, that means the less accurately we know it, the less uncertainty there is in the momentum of the particle, and vice versa. So we can see it's like a seesaw. When one quantity goes up, the other goes down, and when one quantity goes down, the other goes up. Mathematically, we can write this as delta P into delta X is always greater than or equal to h by 4 pi. That means that the uncertainty in momentum, the delta over here shows us the uncertainty, P is the momentum, and the product of the uncertainty in momentum and the product of the uncertainty in position is always greater than or equal to h by 4 pi. That means that the uncertainty in both of them combined has to always be greater than a certain quantity, which is this h by 4 pi. Over here, h is the Planck's constant. Now we don't really need to know what it is, where it comes from, but all we need to know for this is that its value is of the order 10 raised to the power minus 34, which is very, very small. And that is why we can't observe this effect in real life. And we'll discuss a little bit more on that towards the end. Now, to understand where this principle comes from and how it comes, we need to understand that this principle is linked to the wave function of the particle. What is the wave function? The wave function itself doesn't have any physical significance, but the square of the wave function at a particular location gives us the probability of finding that particle at the location. So the more is the square of the wave function, the more likely we are to find the particle over there. And the lesser is the wave function, the rarer it is to find the particle over there. Now, since we know that the wave function and the square of the wave function are directly proportional, we can just refer to the fact that the higher the magnitude of the wave function, the more probability it is we have of finding it there, and the lesser the magnitude of the wave function, the rarer it is to find there, just for the sake of simplifying our explanation. Now, the second thing we need to know is that subatomic entities act as both waves and particles. When we look at something as a wave, we know that it has a certain wavelength. What is the wavelength? It is the distance between two consecutive peaks or two consecutive valleys. Or if you like the word crests and troughs better, it is the distance between two consecutive crests or two consecutive troughs. Now, using something called the de Broglie's hypothesis, we know that the wavelength of a particle is related to its momentum. The higher the wavelength, the lesser the momentum, and the shorter the wavelength, the higher the momentum. So, to understand this better, let us look at some wave functions. Now, if I show you this wave function and I ask you, okay, tell me the wavelength of this wave function. You'll say, that's very easy, Brinda. It is this distance, the distance between two peaks or the distance between two valleys. Great. But now, if I tell you, okay, tell me the momentum of this particle for which you need the wave, tell me the position of this particle. You'll say, I can't really tell you that because everywhere there is a non-zero probability of existence because the wave function has some value. So it can be here, it can be here, it can be here, it can be here, it can be anywhere really. So with this graph, we can determine the wavelength, we can determine the momentum, but we can't determine the position. Let's go to this graph. Now over here, if I ask you, okay, tell me the position of the particle in this graph. Well, yes, there is a little bit of non-zero probability existence here, but we know that if we are most likely to find the particle in this region, somewhere over here, because of the high value of the wave function. And I say, okay, yes, that is true. But now if I ask you, tell me the wavelength of this wave function, you'll say, how do I do that? There are no consistent peaks or no consistent valleys. So I can't measure the wavelength using this wave function. So over here in this graph, we can determine the position. What do we infer from this? That if we want some knowledge about both the momentum, that is the wavelength that we need to find the momentum, and the position of a particle, we need to change the wave function from an infinite sine wave to something that is more localized. Now for this, we need to keep adding similar waves. Let me show you how we do that. So let's say we have this wave function. Now I add some more similar wavelengths to this and superimpose it, and I keep adding, and the center graph is the resultant graph, so you keep an eye on that. So I keep adding the wavelengths, I add more and more, and that's what we see. So we started off over here and we see that the wave function is getting slightly more localized over here. Now to make it even more localized, we need to add a lot of wavelengths. So I'm going to show you that using a different graph of wavelengths. So if we see, there is one wavelength present in the beginning and we have equal probability of existence, that is a non-localized wave function at the beginning. We add more wavelengths and we see that our wave function gets more localized. We add more wavelengths and we see that our wave function gets even more localized until we add infinitely many wavelengths and we see a very localized wave function for which we can tell the position. So for this we can tell the position, but now if I ask you the wavelength of the momentum, you can't tell me because we added infinitely many wavelengths over here and hence we can't tell the wavelength or the momentum. And that is how where we observe the Heisenberg's uncertainty principle. The more accurately we know the position, which is in this graph, the less accurately we know the wavelength. And if we go back and see this graph, the more accurately we know the wavelength and hence the momentum, the less accurately we know the position. Now, with this, now we understand somewhat intuitively what the Heisenberg's uncertainty principle is. One thing we need to keep in mind, and that most people have a misconception with, is that the Heisenberg's uncertainty principle exists because we lack the means to measure things correctly. But that is not true. The Heisenberg's uncertainty principle exists because of the wave-like properties of matter and the matter-like properties of waves that are observable in subatomic particles. It is a fundamental quality of this world that won't change no matter how our sciences advance. And which is why we should know that the Heisenberg's uncertainty principle is a fundamental property of nature and won't change ever. Now let's look at a few more important points before we wrap this lecture up. The first is that h is very small, which is why it doesn't matter for particles which are subatomic. What does this mean? This means that, okay, so we discussed that delta x into delta p is always greater than or equal to h by 4 pi. Now what is p? P is momentum. For quantities which do not have a velocity of light, we can write momentum as a product of mass into velocity. Now, if h is very small, the minimum product of delta x and delta p has to be very small, right? But for non-subatomic particles and things in daily life, for example, a basketball, the mass is very high. Hence, we somehow already overcome the h by 4 pi minimum quota, and that is why the uncertainty principle cannot be observed because the uncertainties are very, very low. Now, another point is that, as if you remember, we started off this discussion with the fact that position and momentum is just one of the examples of the uncertainty principle. Another similar example is that of the energy of a particle in its lifetime. Where do we observe this? We observe this in, let's say, lab synthesized particles or radioactive particles, where the uncertainty in their energy and the product of the uncertainty of their lifetime is always greater than or equal to h by 4 pi, which is the same principle. So, thank you. I am Brinda Dhingra. I hope you understood what I was trying to say, and I hope you're a little bit more interested in the world of quantum mechanics because of this lecture. Thank you for sticking it out with me.